Welcome to Pomodoro Joe for Monday, February 13th, 2023. Today we're looking at LeetCode problem 1523. Count odd numbers in an interval range. This is an easy problem. And the problem statement says, given two non-negative integers, low and high, return the count of odd numbers between low and high, inclusive. Okay, they have some examples and then they have constraints. This can go up to 10 to the 9th. All right, so that's pretty straightforward. We just need to find all of the odd numbers between low and high. So with that, we'll put 25 minutes on the Pomodoro timer and get started. All right, so I'll have some result and I'll start at 0, and then we'll just say for every n in range from low to high plus 1 because it needs to be inclusive. And then we'll say if n mod 2 is equal to 1, then we'll say result plus equals 1, and then we'll return our result. And then we just run that. Psych! Just kidding. That would be a terrible algorithm. It would probably work. In fact, we will try this at the end just to see how bad it is. But this is really more of a math problem. This is not really a programming problem necessarily. It's more math. There's a little bit of logic involved, so that's probably why you can consider this a programming problem. So what do we know about ranges, especially integer ranges? We know we can start at 0, go to 1, 2, 3, 4, 5, etc. If you just look at this, you can see that every other number is odd. So 2, 4, 6, 8 are going to be even, 3, 5, 7, 9 are going to be odd. So every other number is even and every other number is odd. So that means that in any range, about half the numbers are going to be even and the other half will be odd. Now I say about half will be even and about half will be odd. That's because this is really going to depend on which numbers start and end our range. Let's just break this down into some examples. If we say 1, 2, 3, 4, 5. Well, how many odd numbers are in this range? We have 1, 2, 3 odd numbers. That's 1, 3, and 5. And how many even numbers? We have 2 even numbers. So this range starts on an odd number and ends on an odd number. So we actually have sort of a bonus odd number or 2 bonus odd numbers depending on the way you think about it. You could also say, what if we did 2, 3, 4, 5, and 6? Now it's the same number of numbers, just starting on an even and ending on an even. And in this case, we only have 2 odd numbers, 3 and 5. So what I'm seeing here is we have different numbers of odd numbers based on whether or not the range starts at an odd number or an even number. Okay, another way to think about it is, so if you start on an even number and then end on an odd number, you know exactly half of these numbers will be even and the other half will be odd. So 2, 4, 6 are even, that's 3 evens. 3, 5, 7, that's 3 odds. Now let's say if we started on an odd number and ended on an even number. So let's see, we'll start at 1, 2, 3, 4, 5, 6. Again, we have 1, 2, 3 odd numbers, that's 1, 3, and 5, and 1, 2, 3 even numbers, 2, 4, and 6. So if you start on an even and end on an odd, or if you start on an odd and end on an even, you know that exactly half of the numbers will be even and the other half will be odd. Now the other cases are you start on an odd and you end on an odd, then you get 1 bonus odd number. That's like saying half the numbers will be even, half will be odd, plus 1 extra odd. So you can think of it as this first part, which starts on an odd and ends on an even, which we've already determined means that half the numbers will be even and half will be odd. So you can say there's 2 odds and 2 evens in this first part, plus this 1 bonus odd at the end. You can sort of do the same with the evens. If you start on an even and end on an even, that's just like saying you start on an even, end on an odd, plus 1 bonus even number at the end. So in that case, it'll just be half the numbers of the range minus 1 will be odd. Okay, so let's actually figure out the math here. So we will have a result. we'll set it to 0 to start, and we'll return our result. We will probably optimize this by replacing our result with just a straight up return, but for now, we'll keep the result as this intermediary variable. So what do we need to know? Well, we do need to know how many numbers are in between low and high. So let's call that the nums count, or num count. That's going to equal high minus low plus 1, because it's inclusive. So, for example, if we had 1, 2, and 3, there are 3 numbers in this range, and if we said 3 minus 1, we would only get 2. So we actually have to say inclusive plus 1. All right, so now we have the numbers of numbers, and we've already determined that half of them will be even, half will be odd, unless we get a bonus odd number. So let's see. Half will be, I'll call it half count. That's going to equal the num count divided by 2. And let's do an integer divided by 2. And now we have to check, do we have an odd at the start or the end? And if we do, then we get this bonus odd number. So if low mod 2 equals 1, or, oh, sorry, wrong language, or high mod 2, then we will add a bonus number. So our result will, let's see, let me put the result up here. Instead of calling this half count, we'll call this result. And in here, we add 1 because we get this bonus either at the start or the end. Okay, I think that should cover it. Yeah, let's try that. Okay, that seems to work. Let's give it a shot. Oh, and we get a wrong answer. Actually, I was afraid that I kind of knew this was going to happen. This all has to do with this inclusive bit right here. So this has to do, I think, with sort of the rounding of our num count. If we just said, let's see, 1, 2, 3, 4, 5. So there are 5 numbers in this range. 1, 2, 3, 4, 5. And we say 5 minus 1, so that's high minus low, plus 1, so that's 4 plus 1, we get 5. But I don't know if you remember, I did this thing where I separated these, and we had the beginning part plus this bonus 1 at the end. That's kind of what we're doing here, but we're keeping that bonus in our count. So let's take care of that, and let's remove that extra 1. Let's see if we still get the right answer when we run this. Oh, let me remove my comments. Let's try that. Okay, let's see if this will pass. And we pass. Our algorithm is kind of slow. I'm a little bit surprised by that. Well, I guess because we have intermediary variables. So we beat 23% for runtime and 50% for memory. Let's see if we can make some improvements on this. Oh, and then I will go back to our initial solution that did the for loop. All right, so let's get rid of our result. We don't really need this result. And our num count we're using really just in one place, so we don't need to keep the num count. So let's just keep high minus low, and we'll move that in place here. And we can get rid of our num count. We still might want this result. Yeah, we could try that. We could try that. Keep the result for now. Doesn't really make much difference. In fact, we did worse with our memory. That's surprising. Okay, last thing that I'll try. So instead of having this result at all, we can pretty much just say, we will always return this plus 1 if we have an odd at the beginning or end. Or I'll put the 1 first so I don't have to deal with too many parentheses. And we'll always return this otherwise. And then we can get rid of our result. We don't even need this. Now we're cutting this down to just 3 lines of code. Let's see if that still works. All right. Okay, significant improvement on our runtime. We beat 88% for runtime. We're still only beating 7% for memory. A little surprising because we're not using a ton of memory in here. But hey, let's see what the alternative would have been if we had done the for loop. So let's see, that for loop was, we'll have some result, started at 0, and then we'll just say for our number in range from low to high. In this case, we do need to add the +1 to make it inclusive. Then we say if our n mod 2 is equal to 1, then it's odd, and we can say result plus equals 1, and at the very end we will return our result. Okay, it works. Let's see if we can we can even get past the runtime requirements. Oh, and we can't pass the runtime requirements. One thing we could do to optimize this, we already know if n mod 2 is equal to 1, so n mod 2 for an odd value will be 1. N mod 2 for an even value will be 0. So we could actually just say, let's add result. We'll add n mod 2 to our result. So for even numbers, we're just adding 0. For odd numbers, we'll be adding 1. It's kind of what we want. So let's try that. Will this pass? We are eliminating one if statement, so this might actually save us enough time to pass. And it does not. All right, well, as you can see, approaching this from the straightforward coding standpoint, just following the instructions here, not going to cut it. You got to think a little bit further. Think about the math. Think about how you can break this down into a simple equation rather than having to go through this entire loop every single time. All right, folks, that's enough. I've wasted enough of your time on this one. A lot of wrong answers, false starts. Our best algorithm was an 88% runtime. No, it's not too shabby. All right, hope you enjoyed this, hope you had fun, hope you learned something. Try this one on your own, play around with it. This one's a fun one just to sort of dabble, play. It's fun. All right, that's it for me. Please go out and write some better code.